This problem is called letter wheels, and the problem is to determine for 3 separate strings what rotations of those strings work, where work means that in no column there's an identical character. Okay, so each string has got A, B, and C in it, and we want to be able to rotate them, so we're going to actually wrap them around, so the end goes around to the beginning. Okay, and it's pretty straightforward to check whether for 2 strings they're compatible or they work, and that is you just simply scan it, and if you see the same character in the same position, then you know that's a false. You can't do that. So if I was going to write this code, the naive solution is just to iterate for all possible offsets of the second string versus the first. Does it work? And if it does, then we try all possible offsets of the third string against the second. And if that works, then what we do is we need to compare the first string against the third string. If we've already defined the offset between the first and the second and the third, we know what the offset needs to be between the first and the third. It's just the sum of those, the absolute value of the sum of those. So we can check that. And if that works, we're good. Okay? And we iterate through all possibilities and we calculate the minimum. This is straightforward code, and it works very well because it's nice and simple. Unfortunately, it's not very fast. So the statement where we check here if A and B are compatible, we're going to execute that order of n times. And this statement in here, inside the inner loop, we're going to execute that potentially orders of n squared times. Now this check itself is linear, so the total thing is going to be os of n third, os of n to the third, and that's not going to run in time. So we need to improve that. But before we get on how to improve that, let's talk about this where we check for the minimum. What does that mean? What are we doing there? So I've already said that the sum of the distance between the second and the third string, the distance between the first and the third string can be calculated from the distance between the first and the second, and the distance between the second and the third, according to this calculation. But our total cost is actually just the number, how much we rotate the first string, how much we rotate the second string, and how much we rotate the third string, the sum of those things. So how do those relate? Well, it turns out that this expression is minimized when one of these rotations is actually 0. And you can conceptualize that. You think about it. If I'm rotating these wheels, and one of them's rotated to the right, and the next one's rotated to the right, and the third one's rotated to the left, well, if I rotate the top 2 by the right, 1 less, and rotate the bottom by the left, 1 more, I've actually decreased my number of rotations. So eventually I'm going to get to the point where one of these is equal to 0. Okay? If one of these is equal to 0, then we can put that back in this equation, and we know that our optimal minimal spins is going to be the minimum of one of these 3 equations. This one has the B rotation set to 0, so we just add d sub AB and d sub BC. This one has the A rotation set to 0, etc., etc., etc. So this is how we go from DAB and DBC to our actual cost function. Okay, so that was easy. But this OK function, the one we're actually checking to see if it's compatible, that check is os of n, and that's our problem. So how do we resolve this? Well, if in doubt, pre-compute cache. So we simply pre-compute this function for all 3 pairs of strings, A versus B, B versus C, C versus A, and all possible offsets. We can do that in os of n squared, store them in an array, and then inside our inner loop, where we're actually checking to see if something's okay, we just do an os of 1 array lookup, and we're done.